The comparison of energy usage for mechanical vacuum systems to those using compressed air isn't always as simple as it seems. Very often the two technologies are improperly and unfairly evaluated. It's not always as easy as comparing catalog data and making generalizations based on ratings. It's very common to assume that the energy required to operate the mechanical pump is the same as the rating shown on the nameplate of the pump. But actually what's shown here is the horsepower output of the pump, or the brake horsepower. The energy that's required to operate the pump isn't given, but needs to be measured to be accurate. This demonstration uses a watt meter to monitor the electrical usage of the pump. Now we also know that mechanical pumps are not designed to turn on and off as they operate. So when vacuum isn't needed at the cup, it's typically shut off using a valve in the vacuum line, and the pump continues to run at 100% duty cycle. This means that the pump consumes energy even when the vacuum is not required. Let's take a look at what the energy does during a typical vacuum cycle. Here, when the pump's operating open to atmosphere with nothing on the cup and no load on the motor, it's consuming about 510 watts, which roughly corresponds to the 3/4 horsepower that we saw on the nameplate. Now when we put something on the cup is when the vacuum system's in demand and doing work, the energy input rises. In this case we're handling a corrugated material which is porous, so the vacuum level isn't really as deep as a sealed system, but the pump is now using about 740 watts, which is much higher than the rated 3/4 horsepower. Now when we want to release what's on the cup, we have to block the vacuum flow to the cup as well as open a passage to atmosphere so that the vacuum will be broken inside the cup. And we're going to do that with this vacuum valve. Now when we do this, the energy jumps up to over 830 watts, well over 1 horsepower. It's a little bit ironic that in this state, the pump is using its most energy when it's doing no work at all. Also consider that any time the machine is paused, such as if there's a line stoppage or a mechanical jam or no demand on the machine, the pump is always running, very often in this position where it's using the most energy. What this illustrates is that the true energy consumption of this type of pump is going to be determined by how it's run. It's very application specific and application dependent, and shouldn't be an assumed constant that can be estimated just from the pump specs. Vacuum generators, such as seen here, run on compressed air. They're designed to be turned on only when the vacuum is needed. The valve to control the vacuum is located on the energy side, not the vacuum side. When vacuum isn't needed at the cup, no energy is being used. This is true not only for the normal operation of the machine, but also when the machine is paused for any reason, energy shouldn't be consumed by the vacuum system. Again, this means that the energy consumption of an air-driven pump is also very application specific. It should be calculated or measured by allowing for the duty cycle of the application, accounting for when the pump isn't in the operation as opposed to straight air consumption values from the catalog. When using compressed air, you can also adjust the supply pressure to the pump to help optimize its efficiency. The gauge here shows the supply pressure, and by lowering it, it will affect the vacuum level, as shown here, but you still can adjust it down so that you have a very safe handling system. Anytime you can lower the supply pressure, the air consumption will be reduced. Now another feature of an air-driven generator is that while they're smaller and quieter than a mechanical system, they can be mounted much closer to the application. Doing that, being closer, the performance is better because less system volume, fewer potential restrictions, less loss through the vacuum tubing. And this is one reason that too often generators are sized to be exact replacements of a mechanical system, where they can usually be smaller, give the same performance at the application, and naturally use less energy. I hope that the concepts shown here will help the process of accurately and fairly evaluating the energy costs of different vacuum systems and help with designing optimized, energy-efficient vacuum systems.